Hello class, today we're going to be looking at reliability and validity. Often in psychology we use a bunch of measures. These measures are used to give us empirical values to abstract concepts in psychology. For instance, if I have a personality measure, it's going to give me numbers, and these numbers are going to be tied to abstract concepts like introversion or conscientiousness. So I'd have a number that tells me I'm introverted or a number that tells me I'm conscientious. Now, the best measures accurately and consistently represent the underlying abstract concepts that we're trying to measure. So if I take a personality measure, it should be accurate. It should measure what my personality is. If it doesn't measure my personality, if it measures something else, then that's not a good measure. It also should be consistent, both in the test and between repeated trials of the test. So if I have a measure that if I take it multiple times it gives me wildly different results, well, that's an inconsistent measure. And that's not going to be useful. It's going to give us really bad data. And as you can see, these weak measures can hinder the models we want to create. If we have models that are inaccurate or inconsistent, our experiments we're trying to run are going to have a lot less power than if we had an actual good measure. So it's important to have a really useful measure. Now, since we know it's important, we have to think about how can we get the best measure possible, and how can we figure out if we have a good measure or a bad measure. Well, we can quantify the quality of our measures using the concepts of reliability and validity. Reliability basically asks one question: does our measure give us the same result over repeated trials, both within the test itself and within repeated trials, or repeated test taking of these measures? Now, some amount of unreliability is expected. I wouldn't expect that when someone takes a test, if they take it a second time, they get the exact same answers. But I expect it to be similar. I expect the trends to be similar. So people who score high should consistently score higher, and people who score low should consistently score lower. The more consistent the measurement, the higher the reliability. Validity is asking the question, are you measuring what you're trying to measure? So for instance, with personality, if I have a personality questionnaire that's not measuring personality, it's not a valid measure. It's important to make sure that you're not measuring a different construct than the one you're intending to examine. So I could potentially have confounds in a measure. So I might have a personality measure that not only measures personality, but measures what that person's mood is at the time, or measures how anxious they are during test taking. And those things could be confounding the measure. So we could be looking at more than one underlying construct that we're measuring, or potentially we could have a measure that's just not measuring what we're trying to measure. Now, as you can see, validity is much more theoretically driven than reliability. Reliability is a much more mathematical approach, where validity, you have to look at both the statistics and you have to look at the theory behind what you're trying to test. Now, a measure can be reliable but not valid, and it can also be valid but not very reliable. So I brought up this picture that has unreliable and invalid, unreliable and valid, reliable and not valid, or both reliable and valid. So you can see how both changes in reliability and validity can affect your model. Now, if something's unreliable and invalid, you'll notice the scores are all over the place and they're not hitting our construct. So think about this bullseye as the construct or the phenomena we're trying to measure. You could also have something that's unreliable but valid. So this is valid, it's sort of centered around our construct, but the scores are all over the place. Now you can have something that's reliable and not valid. This is a lot easier to see than something like this, because unreliable and valid still gives us bad measures. But something that's reliable and not valid, it'll give us what looks like a good measure. It'll be consistent, but the problem is it's consistently wrong. So we have a consistent measure that's not looking at the concepts we're trying to measure. What we're trying to find is something that's both reliable and valid. We want to see this consistency, but we want to see this consistency that's actually measuring our concept. Now, when we're looking at these sorts of things, what we're going to approach is random error and non-random error. With random error, we're going to see error that does not consistently overestimate or underestimate the model. The error should be unpredictable. The more random error we have, the less reliable the measure. So if we have a bunch of random error, we have a very unreliable measure. If we have very little random error, we have a reliable measure. All measures contain error, but it's important to understand how much error you have. There's no way to get a perfect measure, but we can try to get our measure as good as possible. Now, this random error, again, is unpredictable. Now, this differs from non-random error. Non-random error is error that has systematic bias. So, for example, a reaction time measure that shows consistently slower reaction times than what we should observe is showing non-random error. Or let's think of a thermometer that consistently shows something that the temperature is 4 degrees higher than it should be. It has error, but that error is systematic. It's always overestimating the temperature. The presence of non-random error can show us the presence of invalidity in our measure. So if we have a lot of non-random error, we probably have a measure which is not quite valid. If we have a lot of random error, we probably have a measure that's not very reliable. Now, there are different types of validity. I'm just going to go over the topics first, and then we're going to go into detail over each of them. We have criterion-related validity, we have content validity, and we have construct validity. Now, validity, it lies in the interpretation of the data, not necessarily the measure itself. So, if we have a measure, the measure itself could be valid, but it could be valid for something that we're not looking at. So, if I use a personality measure, but I'm actually trying to look at, let's say, someone's mood, then we have an invalid use of the measure. So when we're looking at validity, we have to look at our measure and how our measure is designed in our experiment. The first type of validity that we're going to look at is criterion-related validity. Criterion-related validity is how well does this measure correlate with information present from other relevant external variables. So for instance, if I was looking at something like driving, making a measure of driving performance, I could see, does my measure of driving performance predict how well people are rated during their driver's license exam? So it's a very intuitive form of validity. We're just seeing, does our measure predict another external variable? Now this comes in two different flavors, concurrent validity and predictive validity. With concurrent validity, we're looking at, does this measure correlate with a criterion that's present at the exact same time? And with predictive validity, we're seeing, does this variable predict a future criterion? The logic between both of these is exactly the same. The only difference is the criterion present at the same time as the measurement, or is it present in the future? An example of predictive validity, for instance, would be, how well do scores on a college aptitude test predict college GPA? So a college aptitude test, let's say like the ACT or the SAT that's taken in high school, how well does that predict college performance? Now, as you can see, this is a very intuitive and easy to grasp type of validity, but it does have limitations. First of all, since we're just running correlation, as you know, correlation doesn't necessarily mean causation. So we don't necessarily know that the measure and the criterion we're trying to look at are causally related. Also, the goodness of your model for criterion-related validity is dependent on how well the criterion is measured. So for something like driving performance, it's somewhat easy to measure that criterion. But as you get more abstract to stuff like, let's say, personality, measuring your criterion becomes more and more difficult. So if you can't adequately measure criterion, for instance, I can't adequately get enough measures to say exactly what someone's personality is, it's much more difficult to look at your measure and compare it to criterion, because that criterion itself is hard to measure. So again, the more abstract your criterion become, the more difficult it is to use criterion-related validity. Another type of validity, let's see if I can pull it up, is content validity. Content validity refers to how well does a measure reflect the domain of content. When you make a measure, it should encompass all aspects that are necessary in defining the construct. So for instance, if I'm looking at an arithmetic test, I can't just have a test of addition because that wouldn't encompass all of arithmetic. I'd have to have a test that includes addition, subtraction, multiplication, and division, etc. Because that encompasses what our idea of arithmetic is. As you can see, this is a very theoretically driven concept of validity. So for example, a measure of academic achievement shouldn't only look at students' grades on a math classes, because our idea of academic achievement, our theory of it, isn't just math grades. It includes reading grades or extracurriculars. There's all sorts of things that we'd use to attribute to academic achievement. Now, as you can see, the more abstract our content becomes, the bigger our domain becomes. And when we have a larger and larger domain, it's harder to get a measure which accurately reflects all portions of the domain. It's really hard to look at every single facet of the domain. But in these cases, it's safer to have more items than less items. So let's say, for instance, I'm looking at personality again. It's safer for me to have too many items and some of them not relate to what we think about as personality, and we could just remove those later, than to have too few items. So let's say, for instance, I had too few items, and when I was making a measure personality, let's say I made a measure personality and I didn't have any information on conscientiousness. Well, at that point we are violating content validity. And since we have too few items, we can't retroactively go back and add items. Whereas if we had too many items, we could have just removed those. So always when you're making these sorts of measures, be on the safe side and have more items than you think might be necessary. And as with criterion-related validity, it's difficult to assess content validity on abstract phenomena. Things like personality, things like intelligence, they can get very difficult to measure easily. And when domains get really large, let's say I was trying to make content for something like sociability. That's a very abstract concept. It's hard to make sure that you have all aspects of sociability. So we do run into these challenges a lot in psychology, where content validity is difficult to have adequate in a measure. The third type of validity that I'd like to look at is construct validity. This type of validity fits a lot better in psychology. With construct validity, we're looking at, does the measure we have predict results on measures which should be theoretically relevant? So what we do is we have our measure, and our measure sits in a theoretical framework. Let's say I made an intelligence test. The idea of intelligence, or the concept of intelligence, should relate theoretically to a bunch of different things. So for instance, maybe I think the concept of intelligence would be related to job performance and socioeconomic status. So I might think that people who are more intelligent may have better job performance, and they may have higher socioeconomic status than people who are less intelligent. So what I should see is my intelligence measure should predict what I think intelligence would predict. So my measure of intelligence in this hypothetical situation should correlate positively with both job performance and socioeconomic status. Construct validity involves 3 steps. First, you have to have a theoretical relationships between the concepts established. So first I'd have to have a theoretical framework. So I'd have to have a theoretical reason why I think intelligence would relate to job performance. Then we would have to examine this relationship. So I'd have to get my measure and see how that performs with, or how that correlates with both in the case of what we're talking about, jobs, job performance and socioeconomic status. And thirdly, we need to interpret this evidence. Now, as you can see, this is a very theory-driven measure. This type of validity is driven by your theoretical framework. And I use two examples for this, but there's a bunch of different things that intelligence could be linked to. So every single time you run one of these tests, you get another piece of evidence. So with construct validity, you're continuously running additional tests and looking at additional relationships, so you get more and more evidence. When you have a bunch of evidence that's linking positively with your framework, you're showing more and more construct validity. So the more evidence you get, the more you're proving that your measure is a good measure. One big limitation of construct validity, though, is that a failure to find a relationship doesn't necessarily mean it's a lack of construct validity. So if I looked at, for instance, my intelligence measure and job performance, maybe I don't find a relationship, but in that case, doesn't mean that I'm lacking construct validity? Not necessarily. There are other reasons that this can fail. One reason is maybe our theoretical framework is wrong. Maybe intelligence is not related to job performance. And if that's the case, if our measure is measuring intelligence, but intelligence isn't related to job performance, our measure itself won't be related to job performance. So that can be a problem. If our theoretical framework isn't sound, our construct validity tests could be off. Also, another issue could just be the procedure that we use. There could be methodological errors, which can make us have a false negative when we're looking at construct validity. And thirdly, it could actually be a lack of construct validity. It could be that when we find a lack of information, it's because our measure isn't actually measuring the construct. So as you can see, this is a really useful, really good way to look at validity, but it does have its limitations. It does have its problems. So the best way of getting these sorts of ideas of, is our measure a valid measure, is to look at not just construct validity, but to look at criterion validity and to make sure that we have the appropriate domains in our measures. So we want to use multiple types of validity. We want to get as solid of a framework as we can when we're making our measures and when we're evaluating these measures. And again, not only do we want our measures to be valid, we want them to be reliable. So let's go ahead and look at measures of reliability. Now, testing for reliability is a lot less theory-driven than testing for validity. We have multiple methods of testing for reliability. The simplest one is the retest method, which we'll go over first. Then you also have the alternative form method, the split halves method, and the internal consistency method. We're going to go over each of these one at a time, and I'll have some examples as we go on. First is the retest method. Now we're going to start getting into formulas from here on out, but I'll try to explain as best I can to make them easy to digest. With the retest method, what we want to see is if we give the same test at two different periods of time, similar results. So here we have two formulas. x1 equals xt plus e1, where this is error, the e1 is error, xt is our true score, and x1 is our first test. Here, x2 is our second test, and we have xt again our true score at error 2, another error. So what we'd want is for x1 to be close to, as we can, as equal to x2. So here's another example of what the retest method looks like. We have our idea of a true score. This is basically what's in classical test theory. In classical test theory, there's an idea of a true underlying score. So here we have a true score, and then we have one time of looking at it, and we have error. So here's our first test, and then we have our second test with error. Now, the closer these are related, the more reliability we have. The less these are related, the less reliability we have our test. So if a test is perfectly reliable, our test-retest reliability will be 1. Now that's not going to happen. We're not going to have perfectly reliable tests because there are just some problems that happen with test-retest methods. First of all, measure taken at 2 different points in time can introduce error. So, for instance, taking a second IQ test, a person who takes a second IQ test may perform worse than their first IQ test because they might be fatigued after having all these tests. Or there could be emotional stressors at that particular day. So someone might be super stressed out and they take the second IQ test and do a lot worse than they did their first IQ test. So the IQ test itself might be reliable, but taking it over different times, people are under different conditions every single time they take it. People don't live in like a box where you can control every facet of the environment. So this becomes a problem with test-retest method. It has some unreliability that's just going to be built into it. Also, taking a test twice can impose logistical issues. So if you're trying to do test-retest method, you have to bring a person in twice to take this test. And you can have reactivity. So the very act of taking a test can influence results on another test. So let's say I was giving someone a measure of political information. Well, if that person took that and shows political interest, maybe being exposed to a lot of political information made them more interested in it. So the second time they took a measure of political information, they performed they showed more interest in politics. And that's because of the previous test. So you get unreliability, but the unreliability is caused by the measurement itself. That's what we'd call reactivity. Also, and this is a big problem, a participant may remember the test. So if you give someone a math test and then you give someone a math test again, they might remember the answers. And if they remember them, then you have just a huge confound. So you might get more the exact same results, but it could be just because they remembered what's happened on the previous test. Overall, I'd say the retest method, while the simplest, is probably one of the worst ones you can use to test reliability. Another method, which is a little bit better than the retest method, is the alternative form method. In this sort of method, it's like the test-retest method. However, the second test is not the original test. What you're going to do is have 2 forms, one with the original test and one with the alternative form of the test. The second test should be different, so people just can't memorize what was on the previous test when we take the alternative form. But it shouldn't differ systematically. So for example, if you're doing an alternative form method with a math test to look at the reliability of that math test, you should see similar difficulty and have similar problems. Not the same problems, but similar problems. One way of doing this is to have a pool of questions and to randomly select from a pool of questions to make both the original form and alternative form. So by randomly selecting, by randomly sampling, hopefully you get 2 different measures that are approximately equal. And this reduces the confound of people memorizing what was on the previous test. Now, this has a lot of similar limitations of the retest method. So all the limitations, aside from the memory limitation, applies to alternative form method. And also, it's difficult to make one measure. And if you use alternative form measure, you have 2 measures. So this imposes a very heavy logistical problem of having to create 2 fully comprehensive measures. And it can sometimes be a lot more work than it's worth. Now, what we're seeing right now is having 2 measures can be a real pain. But what if we can just use 1 measure to test reliability? Now, there are a couple methods to do that. One method is split halves method. The split halves method uses 1 test in order to figure out reliability. It does this by splitting the items in your measure into 2 groups and then correlate those groups together in order to figure out how much internal consistency you have in your measure or how much reliability you have within that measure. When you're dividing these items by half, you normally divide them by your odd items and even items to make your 2 groups. You could also divide them randomly. A less popular method is to divide your first half by your second half of your items The reason this is less popular is you can introduce fatigue artifacts if you use this method of division to make your two halves. After you divide your items into two groups and correlate each other, you get what's called a split half correlation. The split half correlation is an underestimated correlation from what your actual correlation value is. In order to get your actual correlation, you're going to use the Spearman-Brown prophecy formula. The reason this is necessary is when you run your correlation with two halves, it's actually looking at what the correlation would be if you had half the items in your measure. So if I was using 10 items and I split into two 5-item groups, I'd be looking at correlation with 5 items, but we actually have 10 items in our measure. So the Spearman-Brown prophecy formula corrects for this and gives us what our correlation coefficient should be if we had 10 items in our measure. Now I'm going to go ahead and give an example of how the Spearman-Brown prophecy formula works. So if you look over here, the PXX over here is your full correlation, and it equals 2 times your split half correlation divided by 1 plus your split half correlation. Now, here's how this works in practice. I went ahead and I used the formula if we were doing a split halves with a split half correlation of 0.5. So let's say we divided our items into two groups and we correlate them with each other and we got 0.5. If we did that, we would go and take 2 times 0.5, which is our split half correlation, divided by 1 plus 0.5. So here, 2 times 0.5 divided by 1 plus 0.5, if we run this, equals approximately 0.67. So as you can see, our correlation coefficient went from 0.5 to 0.67 when we ran the Spearman-Brown prophecy formula. Now this formula presented is actually very specific Spearman-Brown prophecy formula. The Spearman-Brown prophecy formula is actually a more general formula which can be applied to different things, and we're going to go over that next. This is the more general form of the Spearman-Brown prophecy formula. Now with this formula, you have n times the split half coefficient divided by 1 plus quantity n minus 1 times the split half coefficient. N here stands for how many times bigger the item should be. So if we go back, when we split something in two, this 2 right here is representative of twice as large. That's actually the n. So for instance, if we want to see how our split half correlation, so let's say we had 10 items and we had 2 halves of 5. If we want to see how that 5-item correlation would generalize to, let's say, a 50-item test, so that would be 10 times as large, we would just take this n and make it 10. So 10 times the split half correlation divided by 1 plus 9 times the split half correlation. So as an example, if we had a correlation of 0.45 and let's say we had 5 items and we want to see what the test would look like if instead of 10 items, if the test was 5 times as long. So 25 items. 5 times 5 is 25. I would go ahead and take 5, multiply that by 0.45, which is our split half correlation for this, and divide it by 1 plus, again, n would be replaced by as 5, minus 1 times the split half correlation. So you can just follow the formula. If I did this, I would get 0.803. So as you noticed, the split half correlation goes from 0.45 to our extrapolate correlation of 25 items, which is 0.803. It gets much larger. This formula has another very useful use to it, which we'll get into next. Using this formula, we can figure out how many items we need to add to a measure, given our split half correlation coefficient, in order to get a desired correlation coefficient. So let's say our split half correlation coefficient was 0.5. We could and we want to get correlation coefficient of 0.8. We can use this formula to figure out how many more items we need to add in order to get that particular correlation coefficient. Now we're going to run through an example with real numbers, but for now I'd just like to go over what each of the variables are again. N over here is how much bigger it should be, and this is times the split half. So if your split half was 5 items and N was 10, you would need a total of 50 items. The PXX over here is your desired correlation coefficient. So if I want 0.8, I'd put 0.8 there. Same with this over here. And our split half correlation coefficient goes right here and right here. So let's put this in practice. So let's say we have 20 questions. So this would be a split half of 10. So we had 20 question measure, and then we split into two 10-half parts, and we got a 0.3 reliability. So we got a 0.3 correlation coefficient between those two halves. How many more questions would we need to get 0.7 reliability? That's a question I'm asking for the particular exercise I'm doing. So we have our 10 questions in each half, and we got a 0.3 reliability. So what we do is we take 0.3 and put it right here, and 0.3 and put it right there. We have a desired reliability of 0.7. So we put 0.7 right here and 0.7 right here. So this would equal 0.7 times 1 minus 0.3. All of that's divided by 0.3 times 1 minus 0.7. Doing this will give us our N. So I'm going to go ahead and run this formula, and my N is 5.44. So if I have 20 questions, and each half would be 10 questions, and I'd multiply that by 5.44, so 10 times 5.44, that would give us 54.4, or to round up, we need approximately 55 questions in our measure to get a desired reliability of 0.7 if this measure showed with 10 questions split half a 0.3 reliability. Now split halves do have a couple limitations. There's a lot of different ways to split something in half, and that'll give you different correlation coefficients. So using the same data, people could find two different types of reliabilities, or bunches actually. So a 10 question survey has over 100 different ways you could split it in half in order to get split half correlation. One method that people use more often is called the internal consistency method. The internal consistency method, instead of splitting things in half, it uses inter-item correlations instead of subdividing into two halves to get your reliability score. This doesn't require splitting your test into halves. What you can do to this method is you can add items to increase your internal consistency. However, with this particular method, bad items, so items that are actually not predictive, can reduce your internal consistency and can reduce your reliability. So this method is penalized for having bad items that can reduce reliability. This method also uses what's called Cronbach's alpha in order to find internal consistency. So in order to figure out how much consistency there is between each item, it uses what's called Cronbach's alpha. And we're going to go over that now. Cronbach's alpha equals N, which is your number of items, times the average inter-item correlation divided by 1 plus the average inter-item correlation times n minus 1. Now, when you're doing this, you need to get a correlation matrix. So that's what's different from this and the split half method, is in this one you need a set of data to make a correlation matrix. So for this example, what I've done is I've grabbed the table from the book. So they had a 10-item questionnaire and they gave it to a bunch of adolescents and they got this correlation matrix from it. Now what we want here is, if we look here again, we want the average inter-item correlation. So we would add all these items up and we divide them by the amount of items. I think it's like 45 for this particular one. And in order to, once you do that, you get the average inter-item correlation. So if I did that analysis, I would have gotten 0.32. So using this formula, this is a 10-item questionnaire. So I'd have 10 times 0.32 divided by 1 plus 0.32, which again is your inter-item correlation, times 10 minus 1. So for this particular set of data, as we can see with the correlation matrix, we would get this particular Chromebox alpha. So if I run this, I get 0.824 as my Chromebox alpha. Now what does that number mean? Well, Chromebox alpha has some rules of thumb which you can use. Generally, 0.8 or higher is good for our analysis when making measures. If you try to get 0.9, it might be too much work, and it could be incredibly difficult to get that higher than 0.9 Chromebox alpha. In general, 0.8 is an acceptable Chromebox alpha for the reliability of your test. Now again, remember, when you're doing Chromebox alpha for reliability analysis, you do need a set of data, a set of people with the measures, so you can make your correlation matrix. Because without a correlation or covariance matrix, the Chromebox alpha analysis doesn't work. So that about wraps up what we needed for our validity reliability analysis. One thing I want to close with is we have a lot of different reliability analyses, but unlike validity analysis, where it's nice to use a combination of all of them in order to figure out what validity you should use, in general, using the internal consistency method for reliability is probably your best bet. Chromebox alpha in general is acceptable in literature and is one of the best ways to figure out how reliable your measure is. So I'd normally stick with that when you're doing your analysis.